Okay, so we're going to consider some function f from omega contained within the complex numbers into the complex numbers, which is differentiable at zeta if and only if the following is true. And what I'm about to write is exactly the definition of differentiability you've seen many times before, but now we're writing this in the complex field, and it means something very different. So we have the limit as h. I'm going to emphasize that h is a complex number, right, like this, goes to 0 of f of zeta plus h minus f of zeta over h. So this quotient, you know from calculus, you've seen it many times before, you know what it means. This is the completely familiar expression. This looks exactly like the definition of differentiability from the real numbers to the real numbers. Huh? But this is a very different thing, because now we're using the field properties of the complex numbers in writing this, because this thing at the top is a complex number, this is a complex number, we're dividing complex numbers, we're using the field structure of the complex numbers, what it means to multiply or divide complex numbers when writing this. And that changes the entire thing. That makes the entire thing totally different. This is where the subject of calculus of complex valued functions and calculus of real valued functions go on completely different paths. Because simply doing this is the natural definition of differentiability, this is the correct notion. Simply doing this and asking that it exists starts us off on a totally different path, because this means something completely different. And this is what I'm about to explain. Okay, so we say it's differentiable at zeta if and only if this holds true. Okay, and this is the natural and the useful notion, right? This is indeed a complex number because it's the limit of these two things, and they're both complex numbers. And yeah, this should be believable as the natural notion of differentiability. What is the point of differentiability? Differentiability allows us to take something which might be complicated, like a function, look at it on a very small scale where it is simpler. Where we can analyze it, because on a very small scale it looks like an affine function, right? A linear function plus a constant, right? Which is what this thing is ultimately saying. This is saying that as we, well, let's just write it. So this is equivalent to saying that f of zeta plus h is really a lot like this thing. It's like this complex number times this complex number plus this fixed complex number, because we're moving h, right? Plus some small error. Well, if we put the small error, then it's actually equal. Let's use this notation, where this thing goes down to 0 faster than the absolute value of h, right? So I don't need to put modulus inside, I guess I just put h. So this is the error here, and this thing is going down to 0. This. Let's write it like this. So on a very small scale, around the point zeta, we are a lot like just an affine function. This is a linear, complex linear function plus some kind of a constant. Yeah? Cool. So let us develop the consequences of this. So some notation. So we write f of x plus iy as u of xy plus iv of xy. So u and v are just mappings, therefore, from R2 into R. Right? So this is a very common notation. It's very convenient to write them like this. Yeah? And let's see the implications of the definition of differentiability. So let's take complex plane. Here is 0. Oops, but make it bigger 0. And let's take the limit as h goes to 0 of this quotient. But now, remember, we can do this as h goes to 0 in any way, right? Because all the requirement is that h goes to 0. So we go to 0 along here, along the real axis, like this, yeah? So let's start by doing that. So if we look at this thing, then what are we going to do? Let's take the point z to be consistent with this notation. So if f is differentiable at z equals x plus iy, then the following is true, that if we take the limit as alpha goes to 0, let me emphasize that alpha is real, just a real number. Alpha belonging to the real numbers goes to 0 of f of z plus alpha minus f of z over alpha. This thing has to equal to f prime of z. That's the definition. Alpha being real is still a complex number, right? Because the real numbers contain the complex numbers. So this thing implies this thing, right? And let's write out what that means in terms of u and v. So let's call this thing star. So star is equivalent to the limit as alpha goes to 0 of u of x plus alpha y plus iv of x plus alpha y minus u of xy plus iv of xy over alpha. This limit has to exist, right? We can break it up into the real and imaginary parts together. So that's equal to the limit as alpha goes to 0 of this u of x plus alpha y minus u of x y over alpha plus iv of xy or x plus alpha y minus v of xy over alpha. Yeah, just doing some algebra here. Okay, let's look at this. So this thing is meant to exist. It's meant to be equal to f prime of z. And I claim that implies that both this limit exists as alpha goes to 0 and this limit exists as alpha goes to 0. Yeah? So from real analysis, you know that you can't necessarily conclude that, right? Because it could be that if we were just having these two limits and there are real valued limits and we added them together, the limit could still exist, even though the individual limits of the sum of the two don't exist. They just happen that when we add them together, whatever oscillations is canceling itself out. Yeah? That can't happen here because this guy here is on the real numbers and this guy here is on the imaginary numbers, right? So if this thing as alpha goes to 0 doesn't have a limit, there's no way that this guy can save it so that the sum of these two guys end up having a limit together, right? Yeah? Another way to think about this is just to say, okay, we could take this complex number and project it down onto the real numbers, right? And if we did that, then we would not see this guy, and we'd just see here the real part of this, and therefore we would have that this limit would have to equal the real part of this, right? So this thing has to have a limit by itself as alpha goes to 0, and so does this guy for the same reason. Yeah? I don't want to write out this because it's going to take out too long, but hopefully it's going to seem natural to you. If you're in any doubt, write out what I just said in the language of maths. Yeah? Literally write what I just said. Project this thing onto the real numbers. Write out what that means, right? And then project in the complex numbers, and you'll see that this has to be true. Yeah? Okay, so both these limits exist, so we can write this entire limit of the sum is the sum of the limits, and the limit of this thing as alpha goes to 0 will just be the partial derivative of u with respect to x, and this guy will be partial derivative of v with respect to x. So this thing will be u of x xy plus iv xy. So as a consequence of this definition over here is that the partial derivatives of u and v have to exist, at least with respect to x. Cool. Now we're going to do the same thing, but now we're not going to go towards 0 along the real numbers. We'll go along the imaginary axis. So go IB. So, oh, this is not equivalent. There's a one-way implication. Oh, I'm sorry, this is equivalent. This isn't equivalent to this. This is just, this implication is this way alone, right? So maybe I'm going to write this as, say, star star, definition of differentiability, and star star implies that we do the same game, except now we go down with respect to beta. So it's going to be exactly the same as this thing right here. So let's just write directly from this. So we have the limit as I beta, goes to 0, right? And then what we have, we're going to have u of x, y plus beta, plus iv, x, y plus beta, yeah? And then minus u of xy plus iv, xy, like this over IP, yeah? And then same thing, we break it up like this. And then what are we going to have? We'll have, okay, let's just write it out. So we have the limit as IP goes to 0 of u of x, y plus b minus u of x, y over IP plus I times v of x, y plus b minus v of xy over I times b. Yeah? Cool. And then what happens to this? This thing, so note that 1 over I is the same as I over I times 1 over I, which is just minus I, right? Because I times I is minus 1. So this thing over here will now become minus I, and again we can break up this limit of the sum into the sum of the limits, because both of these sums have to, both of these limits have to exist. So then this will be minus I, and now it's the partial of this, right? And then this guy here is just the partial of this. Okay. And this thing, yeah, is also equal to the derivative definition. So it's equal to the same complex number as this thing, yeah? So putting these things together, we get the so-called Cauchy Riemann equations, right? So from this and from this, we have that this complex number equals this complex number. This complex number is the same as this complex number, just from the definition of differentiability. So let's write that. That means that the real parts agree. So this is the real part and this is the real part. So this is true. And the imaginary parts agree. So this is equal to this. So I can write it as u of y is minus v of x. Cauchy Riemann equations. Okay, cool. So this has enormous implications. This says an awful lot. And I'm going to erase the board and we'll talk about what this says in a second. Do the following thing. So given f from omega into the complex numbers, okay, we've just learned what differentiability means. Yeah? So we say something is holomorphic at some z0 if it's differentiable there. So f is holomorphic if at z0 if f prime of z0 exists, and holomorphic on omega if f prime of z exists for all z belonging to omega. Okay, that is standard definition. We also use the words complex differentiable. Yeah? Sometimes you see the words regular used, but that's a bit more old-fashioned. But this is the most standard definition. So it's holomorphic on a set omega if this exists, and typically we'll have omega be open because we need to have a bit of space to move in order to define this notion of differentiability, and omega is open. Okay, all right, cool. And what have we just learned? We've just learned that if it's differentiable, complex differentiable, at some particular point, then it satisfies the Cauchy Riemann equation. So to illustrate the meaning of that, let's do the following thing. So let omega tilde be the set of points in the plane which we get from our set omega. So if we draw omega tilde, it looks exactly like omega, except we're drawing it in the plane instead of in the complex plane, which might seem like an unimportant distinction, but it's actually quite important, as we'll see in a second. Okay, and then f tilde from omega tilde into R2 by f of xy is equal to u of xy v of xy. Yeah, so now we get a function from this region in R2, we get from omega into R2, so that's omega tilde into R2, yeah, in this way. Yeah? And let's talk about what the derivative of this thing is, right? So hopefully you've all studied multivariable calculus. You're comfortable with what the derivative is. The derivative is 2 by 2 matrix, right? And it's given by this. So the first column is what happens when we take the partials with respect to the x, right? So it's u of x, xy, v of x, xy. And the second column is when we take the partials with respect to the y. So it's u of y, xy, v of y, xy. Now, cool. So this guy right here is the general partial derivative for a function from R2 to, start again, it's the general derivative for a function from R2 to R2, but we also know that we have the Cauchy Riemann equations. Let's put them over here. We have that u of x is equal to v of y, and u of y equals minus v of x. So we can rewrite this thing like this. We're going to have u of xy. Right? What will this guy be using this thing? This will be minus. And this guy using this thing will be this. Right? In other words, this is going to belong to the space of conformal matrices. No? Okay, and conformal matrices, as we already discussed, or I already said at least, that are just some lambda times a rotation. So if we have any a minus b, b, a, then this is just lambda times, say, cosine of theta minus sine of theta, sine of theta, cosine of theta, where lambda is just square root of a squared plus b squared, and theta is arctan of b minus b over a. Okay, so these are very special matrices with very special properties, right? They are just rotations times a dilation. It's going to stretch or shrink and then rotate the plane. That's all these guys do, right? So what we find out is that this representation of a holomorphic mapping as a mapping from R2 to R2 actually satisfies a differential inclusion, right? So f tilde satisfies the differential inclusion d of f tilde belongs to the two-dimensional conformal matrices. Yeah? Cool. So, that has a lot of meaning. That has a lot of consequences for what f tilde can possibly be, because what is the point of differentiability? Differentiability tells us about the local structure of the function, right? So we learned this in calculus 1. We take the tangent line. It looks incredibly close to the function. Therefore, we can do things like calculate the square root of 101 by using the tangent line, which we call a linear approximation in this context, right? So that is one of the key ideas of calculus, is to replace something complicated by something much simpler via differentiability. Yeah? In the context of functions from R2 to R2, how does this work? Well, what we have is that if f tilde is differentiable at, say, x0, y0, then what does it mean? It means that if we have some xy near x0, y0, then this thing is equal to the gradient, oops, I'm doing f tilde all the time, which is this 2 by 2 matrix, at the point this thing, acting on this vector, x minus x0, y minus y0, plus some little error. So the error is of order, let's write x minus x0. Let's write it like this. X minus x0, y minus y0, like this. So the error is acting on small vectors where error of w or mod w goes to 0 as w goes to 0. Right? This is the definition of differentiability. Yeah? So we can rewrite this as f tilde xy is this, which gives us this right here, plus order of x minus y0, y0. Yeah, so, and this thing right here is the tangent line, except now the tangent line is an affine mapping from R2 to R2, right? And this part right here is the linear part, so the f tilde of x0, y0 acting on xy. This is the linear part, and the affine part is this vector minus this vector. Yeah? Completely analogous to the tangent line in calculus, right? So if we do the tangent line in calculus, we have t of x is f prime of x, x minus a, plus f of a, right? Which is exactly this thing right here, where the f prime is this is this, and this is this. Yeah? Cool. So, what does that mean? That means that on a small scale, we have this error, which is a lot smaller than the scale that we're working at, right? We have this error, and then apart from this error, we just have a linear map, which is defined by this gradient here, yeah, which itself is a conformal matrix, which is a rotation times a dilation, plus this constant here. Yeah? So what's the consequences of that? The consequences of that are kind of huge. It means that the geometric information or the consequences of that are that on a small scale, the geometric action of our mapping is incredibly restricted. It's incredibly regular. And I'm going to have to erase some space to show you that. Okay, what have we learned? We've learned that when f is complex differentiable on omega, okay, and we write the representation f tilde satisfies this differential inclusion. Okay, and then from calculus, what we know, that means that f of x y minus, or f tilde of x y is okay, plus some small error. Okay, and this guy belongs to the conformal matrices, right? So let's draw a region, okay? Let's take some point where it's differentiable, say this is our x0, y0. And let's consider what the mapping, so it maps it to something like this, and let's say the image ends up here, x0, y0. And let's draw a little triangle around this guy. Let's draw not a good triangle. A little triangle around this guy, like this. Yeah, so if we take our points x, y around the outside of this triangle, like this, yeah, and then we see what happens under the action of f tilde, right? F tilde is mapping things across like this, yeah? Well, what's happening is that the difference between f of x, y and this thing, which is this point over here, which we think of as fixed because we're moving the x and y around, and this guy is just the point we've chosen, so it's fixed. So the difference between these two guys is given by basically this thing, right? And forget about this because it's very small compared to the scale of the triangle, right? Yeah. So as we move this thing along, right, we basically have this thing going on, right? So as we take our little vector here, from here to here, right, it's being acted on by this thing, yeah? And if you think about what that actually means, it means that as we're moving along this line, then the image of it, at least from this part, will be a line, and there'll be some tiny error given by this. Yeah? Yeah, because we move along this thing here, it's just an affine mapping, put it directly into this thing. This is a linear mapping, so we're just going to get an affine mapping out. So as we move along the line, we're just going to get a line. Yeah? So we move along these boundary of this triangle, we're going to have some kind of a triangle, like this. But even more, we have a triangle that's going to preserve the interior angles, right? Because over here, right, this is still behaving like this thing, right? Its behavior is being governed by this thing. And this thing is just a rotation times a dilation. So what will happen to this triangle is that it might be stretched, it might be shrunk, it might be rotated around, right? So it doesn't have to look like this, which is a bit too similar than the first one. It could be sent to some sort of triangle like this. Like this, say. yeah? Or to some really tiny triangle like this. But the interior angles will remain the same because we are acting on it with a conformal matrix, which is just rotation times a dilation. Yeah? And the error that we have will just be from this thing, so it won't quite be a triangle, there'll be some wiggle around these lines, but as we get smaller and smaller, they're less and less noticeable. Right? That's exactly what this thing says. Yeah? So this is an extremely special property. And we are going to prove many spectacular theorems about functions that are one-time complex differentiable and those holomorphic functions because of this stuff. This stuff alone is already putting us in the realm of functions that are extremely nice in many, many ways. So this is where the real subject begins. This is where things get very different.